So we're gonna have this, instead of model drop, will be or. And it's going to be, instead of prep drop, it's going to be or. And then instead of being a train drop, will be an OR. And let's see. So we have not very good either, 28%. And let's see the confusion matrix. So for the confusion matrix, let's change this to, this is going to be ORed. ORed. Do we have any place else? And we're gonna use confusion matrix on that. And again, very, not very diagonally. We want to have them all in the diagonal line. So this again, not very efficient. And let's do another one. This is with the oh hey, one hot one. Okay. A little bit better, 31% for the M1 score. If we actually see the confusion matrix, we get dv dv wait, that is not okay. Sorry, this is supposed to be okay. So let's do the dv. So that will be dv. So we have to do this one. Sorry, I just thought we were gonna do the confusion, but let's just do the logistic regression. So this is going to be a dv copy dv 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 and I think that covers, oh no, right here, one dv. So we still get a 31, a little bit slightly better, but this is kind of off because we do have a lot of features that we kind of took away the values and we're encoding them, so that's kind of throws off the data predictions. So now what we're gonna do, we're gonna talk about the K folds when we actually take the training data and we divide it into K different subsections and we shuffle them to one being the validation, and then the rest of the training part will be the what you use to train it. So we use this case fold to be able to have a much more accuracy on of random values. So we're gonna use the K nearest neighbor for this. We're gonna download the data. I don't think I added that one here, so I'm gonna put the from sklearn data sets. We're gonna import the load underscore its. And we need the features. Oh, I think I spelled this one wrong. Oh, I don't need this part right here because we imported the whole part, so that we don't need that part there. We imported that in the beginning, so we just need to call the method. And then here we're using the K nearest neighbor for that, so we're just gonna put 5 as our hyperparameter, and then we're gonna fit our data. So we're gonna have our X train and our Y train data from the above when you split it. We're gonna predict using our X test. We're gonna do our classification by doing our Y test thread labels equal, labels equal to K and underscore 5 dot classes. And I made the mistake last time to not include the underscore, so I forgot about that, so now I'll remember. So that's a pretty good one, I would say. Let's do another one with, that was a classification with 5. Let's do the same thing, but now with a K fold of 10. So what this is saying is that we're gonna divide our training data into 10 subsections. And what we're going to be doing is we're going to take turns on each subsections to be the validation part. So the reason that we want to use the validation part is because that helps us modify our hyperparameters instead of using the test data. We don't want to use the test when we're still modifying our models to fit our data, because we can modify our models by changing the hyperparameters. And if we use a test, then we actually causing some leakage on the data to the model, and so our model will be it would be biased in a sense, because it's actually we use it to train our model, so we don't want to do that. And we run this one, and we see that this is a 10-fold CV score of 93%. That's pretty good. And then we do the same thing for we run this one to draw it. This is our 5N and the average, so you can see the folds. We had 10 folds, and we can see when those folds validations were the most successful, and that was when we had the 3, the 5, the 7, the 6, the 7, and the 8. So when we use those as validations, we actually had the best performance. And so now what we're going to do is we actually wanted to do it for different types of ends. So we're going to do it for n neighbors when the neighbors is equal to 1, and when the cross validation, y train, and CV equals 10. Are we still doing 10 k-folds? But the only thing that has changed is the number of neighbors. So we're looking at one neighbor. Remember, the k nearest neighbor is that we look at when we want to predict the prediction of a label. We look at the size of the neighbor. So in this case, it's one size. So we're gonna look at the closest neighbor, and from that we're gonna make a prediction of that label. So if we have three neighbors, then we look at the majority of the neighbors that are closest to that label to make a prediction. The next one would be the same thing, but with a 11. So I'm just going to copy and paste, change this to 11. This is 11, 11, 11, 11, and then we're going to run it. And then we have the same thing for 99. So we're going to have 99 neighbors. We're going to look at 99 neighbors to make our prediction. There's still going to be 10 folds. So that doesn't change. And so then we have a score of 0.4. And then we're gonna do the same thing with the logistic regression. So we're gonna have a logistic regression. Log.fit x train y train, and we're gonna do a prediction of log equal to log dot predict x test. We're gonna print the whole classification thing. So I'm just gonna copy what we have up here. I don't want to be doing the whole thing again. I'm just gonna print it here. So that's for the log. So this is gonna be log right here. Log scores for the log, and I think we still want to do one print of the classification report for the y underscore test thread underscore log labels equal to log labels equal to log dot classes underscore. Okay, so we can see the F1 scores 1, and then the false CBIT scores 93%, so that's pretty good. Then we can graph each of them, and you can see the performance on accuracy for all of them. So we just practically plotting all of them in the same graph, all the ones that we just did. We're gonna skip that part right there. We don't need to talk about it. Which of the 5 models have the highest performance during the cross-validation? Well, we can see that the logistic model had a pretty good run. Which of the 5 models had the lowest performance in the cross-validation? Obviously, the 99K nearest neighbor. How do the top performing models across the validation metrics compare to the test metrics? In other words, how does the model perform in problem 33 versus 34? So we can see here that on the k nearest neighbors, when we have the 1 and 2 and 3 k folds, and also the 6 and the 8, we have our best performance for around all the logistic regressions in the k nearest neighbors. And then we have some regulation. So here it's just practically loading some values for the data set, creating a data frame for it. We're going to call it cancer data frame. Data is going to be coming from the cancer data frame because this is just data that is loaded into the Python. So we're just going to extract it. The columns will be from the cancer's data set feature names. We're going to assign our cancer data frame target. So that's going to be what we're going to be trying to predict. The cancer data set target. So this data set is in Python already, so we don't have to do anything with it. It's already there. And then we're practically calculating some values and setting up into our features. And then we're doing the same thing. We're calculating some values for our target as well. And we're going to assign it to our label. So what we're doing is we're assigning values to our features and to our target. We're going to split the data. We're going to standardize it, the data. And now we're going to be able to create a logistic regression for it. So we're using the logistic regression for that. We're going to use 10k folds there. And then we're going to cross-validate. We're practically doing the same thing that we did before with the logistic regression model. So so practically what we're doing is we're going to repeat this what we have up here, but now with a L2 for our penalty. And so instead of being non-scored, will be an L2 model, and then L2. And let's see our value. So it's 88%. The other one's 88% as well. This is slightly higher. Then we're gonna do the same thing for the model L1. L1. Scores L1 and L1 here. And we had a much better score, an 88%. And then here we're just practically just graphing visualizing everything about our logistic regression. So we have everything that we just did over there. We're putting it all at once. So all the training, all the logistic regression models, and then put them together to display the accuracy between each fold. So remember, we have 10 folds right here, and we're showing which one had the best fold. So we can see that at fold number 5, the accuracy was way better. It's almost 95%. And we'll stop there. So so this is the last techniques that we have for machine learning. It's so standardizing it, normalizing it, and encoding it shouldn't be that bad. I mean, there's different ways of removing any any column that doesn't have a numerical value. It's, you can drop it. You can do an ordinary. You can assign it a numerical value. You can do a hot one or a dummy one. Okay, so hopefully that helps, and I'll see you next time.